Hello, I'm Bree Lindsay, Director of Science Services at the California Council on Science and Technology, and I am the moderator for the full scientific session, Improving Community Resilience to Extreme Heat in the Changing Climate. Thank you for joining us. This presentation is one of 3 pre-recorded videos featuring speakers material before all panelists come together in February for the live discussion. In this video, Dr. Michael Weiner will be presenting on the behavior of heat waves in a changing climate. He's senior staff scientist at Lawrence Berkeley National Lab, and I'm going to hand it over to him. After his presentation, we will delve into his material a little bit more, and I'm looking forward to his comments. Welcome, Michael.
Well, thank you very much. As many people know, this summer there was an unprecedented and disastrous heat wave followed by fires in the Pacific Northwest. And it is natural to ask, how has climate change from the human consumption of fossil fuels affected this heat wave, if at all? I'm going to present some work that's been done both by the World Weather Attribution Center, which is a ad hoc group of scientists across the world, in this case over 30, and then some work done by our group, the names of whom you see here at the Lawrence Berkeley National Laboratory. Before I go on, I must make a disclaimer that what I say today are my own comments and do not necessarily represent that of the Department of Energy, the University of California, or the Lawrence Berkeley National Laboratory. So the heat wave, it was right between June and July. Records were not just broken, but were shattered, really unprecedented. Air temperatures reached as much as 120 degrees in Canada. If you had asked almost anybody prior to this event if temperatures of that magnitude could be reached anywhere in Canada, they would have laughed at you. But indeed, it happened. And because things were so hot and so dry, fires followed and destroyed the town of Lytton in British Columbia. In Oregon and Washington, temperatures exceeded 115, again shattering records by several degrees. In fact, satellite estimates can measure the ground. Those were air temperatures I just quoted, but can measure the ground temperature as well. And a temperature of over 145 degrees Fahrenheit was seen in Wenatchee, Washington. Now, this is not without consequences, and Wikipedia reports as the week of this recording that over 1,400 excess deaths were recorded during this period. I'll have more to say about that towards the end. And the World Weather Attribution group published a rapid attribution, I'll talk about this in a minute, saying that such temperatures were virtually impossible without climate change. And you can go to their website to read the detailed report. So in this report, which involved 30 scientists, including me, across the world, on their own time, this is actually a volunteer kind of effort, they made 2 important statements. One was that climate change made this event at least, and the key word is at least, 150 times more likely than without climate change. And that climate change made this heat wave 2 degrees centigrade, or about 4 degrees Fahrenheit, warmer than it would have been if there hadn't been any climate change. Now, attribution is an exercise in which statisticians would call causal inference. And it recognizes that a complicated event, like any weather event, or many other kinds of events that you might experience, have many factors that are important to have all in place. These are the causal factors. And it turns out that this heat wave is a particularly scientifically challenging event. So let me tell you a little bit about extreme weather event attribution, which you may or may not have heard about. It's been in the news a lot lately. And the question is, how much has global warming already affected specific individual weather events today? Not in the future, but today. And to understand these human effects, we borrow techniques from epidemiology, which is another aspect where there's a complicated set of causal factors, and asked these two questions that the WWA answered. How is the probability of this event changed because of climate change, and how did climate change affect the magnitude? So those two questions are actually intimately related. And this figure here is a calculation I did using one of the models we had at Berkeley Lab that showed the probabilities of these events at different magnitudes with and without climate change. The blue curve is without climate change. The red is with, and we can either slice up and down, and which would fix the magnitude and ask what's the change in the probability reading off the y-axis, or slice horizontally, which fixes the probability and answers the second question, how has the magnitude changed? Now, this picture from the WWA report shows what scientists often call the anomaly. So if you see that word, that means actually basically how different it was on this day versus the climatology. And so this is an exceedance of the temperatures on the hottest day of this heat wave compared to the average hottest day of the year from 1950 to 2020, and you can see that it's upwards of 4 degrees centigrade. So it really just was much bigger than what you might expect, and much bigger actually than previous records. So diving into what the WWA did. I must say that prior to this event, I had thought that attributing the human influence on heat waves is fairly straightforward. Now, my good friend, the late Gert-Jan von Oldenburg, actually had thought the opposite, and he is correct. This one was really hard. Generally, the hottest day of the year, these pictures that I showed in the previous plot, was that from a generalized extreme value distribution. This is a statistical theory that talks about how to describe the tails of distributions. And it turns out that if you fit the observed data, which is shown here in this picture here, to the generalized extreme value distribution, the hottest day of the year from 1920 to or 1950 to now, and not include this particular, you don't want to include 2021, you want it to be an out of sample test. Well, you would conclude that these temperatures were impossible without climate change. In other words, that this is a bounded distribution, and that the observed temperature was outside of the bound in 1950. But the problem is that it's also outside of the bound using the 2020 values, and so it would have been the theory with this distribution would suggest that it was impossible even with climate change. Well, it happened, so obviously something is wrong. And so in order to make a statement, Gert-Jan included 2021 and said that, and found that the theory then said that it was about a 1 in 1,000 year event currently, and a 1 in 150,000 year event without global warming. Which is where the virtually impossible statement comes from. And then use that information and climate models to estimate how much cooler it might have, a 1 in 1,000 year event might have been in a pre-industrial climate, and that turned out to be 2 degrees centigrade, or about 4 degrees Fahrenheit. So what makes this event so difficult? Well, it breaks the statistical model, and the values are well above the bounds of the out of sample generalized extreme value theory or distribution. And when you include 2021, then that actually makes the fitted generalized extreme value distribution have a very poor goodness of fit. And why is that? And basically, it's just too much of an outlier. And one of the assumptions behind generalized extreme value theorems are that the data be independent and identically distributed. In a plain language, that means, are the causes behind these events of the same type? And in this case, it's not. And 2021, and this may be kind of obvious, is the result of some very different weather pattern than any other year ever recorded in this area. And this is what you might have read in the popular press is called a heat dome. And technically it's called an omega block because the flow of the atmosphere sort of looks like the Greek letter omega. And it's characteristic of the waviness of the jet stream. And when you have one of these omega blocks, you get the heat dome, which is a high pressure region, and the winds go around it, so you can't transport cooler air into it. And it sits there and gets really hot, and it cooks because of the radiative energy from the sun. Likewise, if you have an omega block in the winter, it gets very cold because you're not bringing warmer air in from outside of it. And then, indeed, this was a very well forecasted event, and so that it at least several days before, it was not a surprise. Several months before, it certainly was unexpected. What is make this event really, why this breaks the statistical theory, is that an omega block in this particular location is likely unprecedented, or at least certainly in our recorded history, it hasn't happened. It may be common in other places lower down, and heat waves in, say, California are often from an omega block, but never in the Pacific Northwest. And so, of course, that makes it scientifically interesting because it breaks all the models. I think it's pretty clear that it's because it's not this IID, this independent and identically distributed kind of event. But it also breaks our climate models because it's really too rare to find in our climate models. Even though we have large numbers of simulations and petabytes of climate model output to analyze, if it's not there, it's not there. It's also possible we're missing some important processes. Jennifer Francis and Steve Vavris have suggested that the jet stream is becoming wavier. And if that is indeed the case, and I think the evidence is not conclusive yet, there would be more blocking events and more heat domes. So what do these challenges mean for attributing the human influence on the Pacific Northwest heat wave? Well, the uncertainty in the attributable change in the risk, the statement it's at least 150 times more common, is actually very, very high because of the fact that the statistical model is not as robust or fit for purpose as it should be. But the attributable change in temperature, the 2-degree statement, that can be estimated in other ways. And what we've done at Berkeley is constructed what we call a storyline simulation. And what we do there is we run a very high resolution weather prediction model, a forecast model, but as a hindcast, so it already happened. And we run it 2 different ways for attribution. We run it as the world that was, so configured as realistically as possible to simulate the event that actually happened. And then a counterfactual simulation, the world that might have been without climate change. We remove the human influence on the climate. That's for attribution. We can also, it's instructive to say what might this event have looked like if it had happened in a warmer world as well. And so we looked at the end of the century under an emission scenario where there is no noticeable reduction in no policies for reduce carbon dioxide emissions. So my colleagues Emily and Travis are running 2 different models, in fact, so we get some idea of how different models respond. And the panel on the left is the simulation of the world that was. The panel in the middle is the difference in temperature between the world that was and the world that might have been had there not been climate change. And we can see that there's some spatial structure. Some places are warmer than others. The WRF model is a bit warmer than the red CM, and I'll talk about that in a moment. But you can see that it's between 2 and 4 degrees centigrade warmer in Oregon and Washington. Not quite as much human influence in Canada. As we go into a much warmer world, you can think of this as a no policy scenario at the end of the century. We're more like 4 to 6 degrees. That would be like 10 to 12 degrees Fahrenheit warmer than it actually was. So obviously it would be even yet more deadly in a world with a lot more climate change. Like I've said, Reg CM is running a bit cooler than the WRF model. Part of this is due to the way we've constructed the two simulations. We couldn't change everything in the Reg CM model, and one of the key things is the soil moisture. What happens in a warmer world is soils are drier because there's more there's increased evapotranspiration that makes the soil drier. What that means is that when you have a heat wave, there's less evaporative cooling because there's less available moisture. And what we found with the WRF model, where we could change these things, this didn't contribute as much as some people might have expected. It was only about a tenth of a degree centigrade. But by the end of the century, it really takes off. The soils get really, really dry, and you lose most of the evaporative cooling that tends to moderate heat waves, and it's about 3/4 of a degree. And the reason I highlighted that is that these storylines allow us to separate many of the causal factors of the Pacific Northwest heat waves. Things we're looking at now are compressible heatings from the downslope winds, the winds that come off of the Cascades in this case, which seems to be a smaller factor than I initially had thought. But then the large-scale compressible heating from subsidence, we can analyze that as well, and our student LEAF is doing that, as well as the horizontal transport of heat from outside of the region. Furthermore, we can get at the not using the storyline, but doing a non-parametric treatment of the observed data, make an estimation of the change in risk that would not rely on a generalized extreme value distribution that is not particularly appropriate. That's all underway, and I thought because of the theme of this session, I should talk about mortality. No, I'm not making estimates about the changes in death, but I am interested in this, and it can be done. And like I said, Wikipedia put this at the time of this recording at 1,400 excess deaths. It's a complicated process to make these estimates, but I'm hoping that peer-reviewed estimates will be made soon. But if we know the amount of warming and we know the number of deaths, we can actually estimate how many of those deaths were due to climate change. It does require professional epidemiologists to develop these mortality curves, but you can see one here on the right here that shows one for northern European cities, and you can see that as the temperatures get hotter, this tends to go up. It tends to get very steep as you get to very high temperatures. And Seattle's record temperature was 108 degrees Fahrenheit or 42 centigrade, so it's off the scale of this. But it would have been 40 degrees centigrade without climate change. And so you could look at this plot and say, there's so many excess deaths at 108 degrees Fahrenheit and so many at 104. Take that difference. That's the attributable number of attributable number of deaths due to climate change. It's likely to be large, but we don't know yet. So to summarize, the 2021 Pacific Northwest heat waves just shattered previous records. And it was because it was such an unprecedented weather event. The flow of the atmosphere was just never been seen like that before. The large-scale meteorology may or may not have been influenced by climate change, but even though with the climate change, we know that there was increased radiative forcing and reduced evapotranspiration, which added about 2 degrees. The best estimate of the change in the risk of this is much less certain. It's clearly very large, and challenges are statistical techniques. And so it's a teachable moment for scientists in that heat waves are difficult. They're not as simple as many of us would have thought. But it's also a teachable moment for the public that dangerous climate change is here now, and that it's not some distant problem for our grandchildren. It is a problem for us, and that people are dying, properties are being destroyed from fires or even floods and other kinds of weather events. And it's something that we need to accept and deal with as quickly as possible to reduce any further suffering. So thank you very much. And now we can go to questions.
Thank you so much, Michael, for your very thoughtful presentation. I have a couple of more, I have one kind of specific question and then some more general questions just about extreme heat events. And one thing I was interested to know about, you were talking about different candidates for causal processes that might not have been incorporated in the original model. And I'm wondering what sort of processes this model is most sensitive to creating something like this, so that what processes seem to be making the biggest impact in these models that are not currently always considered?
Well, the the conjecture that Jennifer Francis and Steve Vavros made about changes in the large scale circulation are really quite interesting. Um, and it's not clear that that it's very interesting idea, and it has caused us to, as a scientific community, to really think harder about how the change in the gradient of temperatures between the equator and the pole. The pole's warm more than the equator, so that changes the way the temperature gradient between as you go north or south from the equator, and how that changes the circulation of the jet stream. And it is pretty clear that the jet stream slows down because a warmer atmosphere is more stable. And what has eluded us, I think, and it's a controversial subject. Some people believe it more than, and some people don't. I'm sort of neutral on it. But if there is a change in this waviness of the jet stream, then we certainly can expect many more extreme weather events, heat waves in the summer, and maybe paradoxically, cold deep freezes like happened in Texas in the winters, but also storms. The jet stream controls the trajectory of storms, and it could bring extreme weather into places that hadn't had such magnitudes of extremes in the past. So I think that's the big one.
Yeah, and so thinking about the jet stream waviness, you were talking about this omega shape and the heat dome, and said that it was really well forecasted. I'm curious how far ahead of time it was forecasted, and if scientists are kind of looking for weather patterns like this to be able to say there is a risk of an extreme heat event of some degree, in terms of warning communities so they can take action. How far ahead are we able to make statements like that?
Well, it depends on what kind of warning you want to give. I'm not a weather forecaster, but I do know that that forecasts a week in advance of very strong events is pretty good. 4 or 5 days is very good, and so this is enough time to implement plans that have already been made.
Mm-hmm.
But if you don't have a plan, it's not nearly enough time. And so what the work that I just showed you can do is tell us that, remind us that there is a clear and present danger here that has been exacerbated by climate change. And so, that's now. This every heat wave that happens from now on in has been made worse by climate change. I'll stand by that statement. In the United States, about 3 to 5 degrees Fahrenheit hotter currently. That will get worse, of course, as the climate warms, which it is going to do. And so science tells us, be prepared. Weather forecast tells us, implement your plans that you've now prepared.
Yeah, that makes sense. And then we have a few seconds left, and I'd love to hear, what is the single most pressing gap in our knowledge that you would like to be able to fill?
I'd like to understand how climate change affects fires better. The number of large Western U.S. and Western Canadian fires has exploded over the last couple of years, and this has significant ramifications both for the people affected by fires. I've had several friends who have lost their own homes, but also for millions of people who breathe the smoke. And there's a clear connection between global warming and these fires, but I think quantifying that change in risk, I think, is an interesting and important thing to do right now.
Yeah, absolutely. Thank you so much for your time today. And just for those watching, this is a reminder that this is one of 3 spotlight videos focusing on the individual work of the speakers before everybody comes together in February for the live panel on improving community resilience to extreme heat in a changing climate. Please check the AAAS annual meeting website for the panel's date and time. And again, thank you so much. Thank you to the audience, and we'll see everybody live in February.
And thank you for having me.